Electricity. The key areas covered will be current, voltage, and resistance, series and parallel circuits, and rules for series and parallel circuits. What we will do today is revise the definitions for current, voltage, and resistance, revise series and parallel circuits, determine the current and voltage at different points in series and parallel circuits, and determine the total resistance in series and parallel circuits. Current and charge. Current, I, is the rate of flow of charged particles. It is measured in amperes, A. Electrons are negatively charged and so flow from the negative side of a power supply to the positive side. To measure the current through a component, place an ammeter in series with it. Ammeters should have a very low resistance. Charge, Q, is transferred when electrons flow. It is measured in coulombs, C. Potential difference. Voltage, or potential difference, V, is the number of joules of energy gained or lost by 1 coulomb of charge moving between 2 points. It is measured in volts. If one of these points is earthed, the voltage is called a potential. The bigger the potential difference, the bigger the current. To measure the potential difference across a component, place a voltmeter in parallel with it. Voltmeters should have a very high resistance. Resistance. Resistance, R, is a measure of how difficult it is for the current to flow in an electrical circuit. It is measured in ohms. The bigger the resistance, the smaller the current. Ohm's Law. Ohm's Law refers to the relationship between potential difference, or voltage, current, and resistance. In equation form, this is written as V equals IR, so voltage equals current times resistance, where V is potential difference measured in volts, I is current measured in amperes, and R is resistance measured in ohms. We can also write this as current equals voltage over resistance, and specifically, the current drawn from the supply is equal to the total voltage supplied divided by the total resistance. For a specific component, we can say the current through a component equals the voltage across the component divided by the resistance of the component. Series circuits. There is only one path for the current to flow in a series circuit. Here we've got a little example. We can see a series circuit and we can see some ammeters in series and some voltmeters in parallel with some of the components and the source. Circuit rules. The current is the same at all points in a series circuit. The supply voltage is equal to the sum of the voltages across the components. The total resistance of the circuit is equal to the sum of the individual resistances. Note, voltage is proportional to resistance, i.e. the biggest resistor takes the biggest share of the voltage. Example, calculate the total resistance of this circuit. As each coulomb of charge has to pass through both resistors, it loses energy in both resistors, so the voltage divides. Our total resistance equals our resistor 1 plus resistor 2. So this is equal to 10 plus 5. Our total resistance here is 15 ohms. What you have to notice is that our total resistance is always greater than the largest resistor present. Parallel circuits. There is more than one path for the current to flow in a parallel circuit. We can see we have 2 resistors in parallel here, a number of ammeters and a number of voltmeters. Our circuit rules are as follows. The supply current is equal to the sum of the currents in the branches. Voltage is the same across each component in parallel. Note, I is inversely proportional to R, i.e. the biggest resistor has the smallest current flowing through it. Example, as each coulomb of charge can only pass through one resistor, it gives up all its available energy in that resistor, so the potential difference across each resistor is the same. Let's check this using Ohm's law. The voltage across the 10 ohm resistor is equal to the current times the resistance, so our current we can see in the diagram is 2 amps and the resistance is 10 ohms, and we can see 2 times 10 is 20 volts. The voltage in the 5 ohm resistor is equal to our current times our resistance, so we can see our current is 4 amps and our resistance is 5 ohms. These multiply together give 20 volts as well. Resistance in parallel. Here we're going to look at our rule for resistance in parallel circuits. We have a circuit here with 3 resistors in parallel. From conservation of charge, i.e. the total charge per second passing through R1, R2 and R3 must equal the charge per second supplied from the cell. So I equals I1 plus I2 plus I3. We know Ohm's law, V equals IR, therefore I equals V over R. Replacing I with V over R in each case gets us V over our total resistance equals V over R1 plus V over R2 plus V over R3. We can eliminate voltage from both sides of this equation, and it leaves us with 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. We can simplify that to give us a general equation as 1 over RT equals 1 over R1 plus 1 over R2, and so on and so forth. You need to note that our total resistance here is always less than the smallest resistor present. Example 1. Simple parallel circuits. In a circuit, there are two resistors in parallel. One resistor has a value of 5 ohms and the other resistor has a value of 8 ohms. Calculate the total resistance. For this, we need our equation for resistors in parallel. This is 1 over RT equals 1 over R1 plus 1 over R2. We can substitute in our resistor values, so 1 over RT equals 1 over 5 plus 1 over 8. And you can either pop this straight into your calculator, the 1 over 5 plus 1 over 8, or you can manipulate the fractions. I'm going to show you quickly how to manipulate these fractions. Both 5 and 8 go into 40, so we can say 8 over 40 plus 5 over 40. And then we can easily add these fractions, so that becomes 13 over 40. To get RT by itself, we invert both of our fractions, so RT over 1 is equal to 40 over 13. We know that anything divided by 1 is just itself, so we can get rid of that over 1, just leave it as RT. And 40 over 13 is 3.076, and so on. We can round this to 3 ohms. Example 2. Mixed circuits. Calculate the resistance between X and Y. Here we can see what looks like 5 resistors in parallel. However, if we look at the top row just here, we can see that this resistor and this resistor are in series with each other. So when resistors are in series, we have to add them to get the total resistance. So on our top row, we have a total resistance of 10 plus 10, which equals 20 ohms. Our middle row, we don't need to do anything to, that just stays as 10 ohms, there's no other resistors there. And our bottom row, we can see again there are two resistors in series with each other. We've got 10 plus 10, again that's 20 ohms. We can now use our equation for resistors in parallel to use these combined resistances to get our total resistance. So 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. R1 in this case is our top row, so that's 1 over 20. R2 is our middle row, so 1 over 10. And R3 is our bottom row, so 1 over 20. Again, we could just put this straight into a calculator, or we could manipulate the fractions. So 1 over 20 plus 2 over 20, that's the same as 1 over 10, and plus 1 over 20 gives us 4 over 20. Again, RT over 1 equals 20 over 4. We've flipped both of our fractions. We can get rid of that over 1 because it's not necessary, and 20 over 4 is 5 ohms.